Good morning. So let's talk about potential energy today. We saw that when you do work on a point object, it only can acquire one kind of energy, and we used Newton's second law to drive a formula for that kind of energy, and it is what we now call kinetic energy. What happens when you apply work to a excuse me? What happens when you do work on a system? Well, we can calculate it a couple different ways. Let's say, for example, that we are going to lift up a 4 kilogram block, and we are going to lift it up a distance of 2 meters, and this is in the presence of gravity, as indicated by that blue globe down there, which is supposed to show you that the Earth is present here. This picture is not to scale. So first, we'll draw a dotted line around our mass and consider our mass to be a separate object. And we're going to calculate the net work done on the mass when we move it up. Now, if we're going to move it up at a constant speed, then the work, the force applied must equal the force of gravity. So we're not accelerating it, there's no net force. And so you could say, well, the net work done is zero. Or you could say the force of gravity, which would be m times g, is doing negative work, and the applied force is doing positive work, and they are in opposite directions. The amount of force would have to be, well, let's see, mg would be 4 times 10 to be 40 newtons over a distance of 2 meters. So the applied force does 80 joules of positive work, but gravity does 80 joules of negative work, and so no net work is being done on the mass. But now, let's identify the system as the 4 kilogram block and the Earth. So we'll draw a dotted line around both of those. Now let's calculate the work done on our system. Well, we still have the same force pulling it up. It still has to be 4 kilograms times 10, so that's 40 newtons pulling it up over a distance of 2 meters, which means that 80 joules of work was done on the system, but we do not do any contribution from the force of gravity, because the force of gravity is part of our system. And so it is not an external force, it's an internal force, and it does no work on our system as a whole. And so the net work is equal to 80 joules. Now wait a minute. Work is a transfer of energy. This thing did not acquire any kinetic energy. We said we're lifting it up at a constant speed. Where did that energy go? Well, in order to understand where the energy went, we're going to need to talk about non-conservative forces and conservative forces. Conservative in this sense has nothing to do with any kind of voting pattern. A force is conservative if the total work it does on a particle is zero when the particle returns to its initial position. So, in other words, work just depends on position. It doesn't depend on anything else. And these conservative forces are part of the system. For example, it's like gravity. Gravity is a conservative force, because if I lift something up in a gravity field 2 meters, I'm doing gravity is doing negative work on that thing because gravity's pulling down and thing's moving up. And then if you lower it down those same 2 meters, gravity is doing positive work on it because gravity's pulling down and the thing is coming down. And the net work done on it when you get back to where you started is going to be zero. So the total work done on it will be zero if it returns back to your starting position. Gravity has that feature. And that's not always the case. Consider friction, for example. Here, this is showing a eraser being rubbed across a smiling face. I don't know why they're trying to, rub the smiling face out, but they are apparently. When that eraser goes from point A to point B, the amount of work done in erasing that smiling face is going to be different if it takes the path going directly from A to B as if it takes the path going from A and then going up and around a little loop and then going up and then back down to B. Friction matters. If I pull a block around my desk in the shape of a rectangle, so I start at one point, end at that same point, when I return at that same point, the whole work done by the force of friction will be a negative. There's no positive work being done on a block as I'm pulling it around, because the friction always opposes the relative motion of the objects, and so it's opposing the motion of that block. Let's take a look at this question. A block slides a certain distance down an incline. The work done by gravity is W. What is the work done by gravity if the same block slides the same distance up the incline? Well, we know that when it returns to its starting position, we want the total amount of work to be done to be zero. And so clearly the work must be a negative W. So this concept is going to allow us to define this idea of potential energy. This is the other kind of energy that things can get when work is done on a system. Let's consider U to be a function that is the potential energy that is associated with a certain conservative force. And let's let W be the work done by the conservative force. So this is the internal work being done by the conservative force, transferring energy from one form to another. Then the definition of potential energy really is how much that potential energy changes. The change in potential energy caused by a conservative force F is equal to the negative of the work done by that conservative force. And here you see that integral notation showing the work being done as the object goes from position x1 to position x2. It is the negative of that integral. Let's look at our one of our examples again in just a moment. First thing we need to do is get a simple formula for the work done in a uniform gravity field. So mostly we've been talking about gravity this year so far, and even last year especially. Most of the time we talk about gravity, it's near the surface of a planet where the gravitational field strength is more or less a constant. So we know that the force of gravity near the surface of the Earth has a magnitude of mg, and it points down, so in the negative j direction. And so the force of gravity is a negative mg in the j direction. And let us say that we have a displacement vector. Here I see delta x, but the x is bolded, so it consists of all three directions of motion, not just x, but x, y, and z. In this case, we only have a j displacement. Let us say that the net displacement is in the vertical direction and a distance h. Well, what is the work done by that conservative force over that displacement? Well, the work is a negative mg times h. So what is the change in potential energy? Well, the change in potential energy is a negative of the work done by the conservative force, so the change in potential energy is mgh. And so this allows us to define a gravitational potential energy. In a situation where the force stays more or less constant, the change in potential energy is mgh, where h is the height that the object was brought to. Let's do this in detail. You can kind of see how this works. If a student tosses the ball with a mass of 100 grams straight up, while she is throwing the ball, she exerts a constant force of 3 newtons on the ball over a vertical distance of 1 meter. And g is going to be equal to 10 today, 10 meters per second per second. How much work did she do on the ball? Well, she does a constant force of 3 newtons, a vertical distance of 1 meter, so that's 3 times 1, that is 3 joules. And how much energy did she add to the system? Well, the work that she did on the ball is the work that she did in the system if we consider the system to be the ball and the earth together. So 3 joules. How much work did gravity do? Well, the ball has a mass of 100 grams, which means the force of gravity is mg, so that should be 0.1 kilograms times 10, so that should be 1 Newton. And the gravity is acting over a distance of 1 meter as well, so that's 1 joule of work. Gravity did 1 joule of work. And gravity did negative 1 joule because it was an internal force within the system. By how much did the system's potential energy change? Well, the potential energy change is defined as the negative of the work done by the conservative force. So the force of gravity, the potential energy must have changed by a positive 1 joule, because it's a negative of the work done by the conservative force, and since it was a negative 1 joule that gravity did, it's a positive 1 joule increase in energy. Now, wait a minute. The student did 3 joules of work, and the system's potential energy increased by 1 joule. What happened to the rest of the energy? Well, it acted like work done on a point object. It went into the kinetic energy of the object. Here's another one we can do. Very similar vein. 0.6 kilogram basketball is dropped out of a window that is 6.1 meters above the ground. The ball is caught by the person whose hands are 1.5 meters above the ground. And just so we are all working on the same sheet of music, let us say that the 0 for measuring potential energy is at the ground level. So how much work is done on the ball by gravity? Well, 0.6 kilograms, that's 6 newtons. And it acted over a distance of 6.1 minus 1.5. So that is 4.6, I believe, if I did that correctly. How much work is done with the ball by gravity? Well, if that's 4.6 meters, then that distance, 4.6 times 6 newtons, should give us the work done on the ball by gravity. And pulling out our handy dandy calculator, I get 4.6 times 6 equals 27.6 joules. What was the gravitational potential energy when it was released? Well, let's just say mgh is our formula. And we're going to use the 0 to be the ground level, so that's going to be 6.1 is our height, and m is 0.6 and g is 10. And so that gives me 36.6 joules of potential energy initially. And then what was the gravitational potential energy when it was caught? Well, that's going to be 1.5 times 0.6 times 10. And that's going to equal 9. And 36.6 minus 9 gives me 27.6, which I believe is what we expected. just to confirm one more time, the work done was negative, but you turn the change in potential energy. Well, sorry, the work done was positive, and you turn it in the change in potential energy is actually negative because it's a negative 27.6. And I think it all worked out. No pun intended. Right, 6 equals times 10. Yep, 27.6, that's what it was. So the change in potential energy was negative, the work done by gravity was positive, but they were the same magnitude. This was our spring potential energy, and here I'm showing the very formal way of writing the potential energy, which is the negative of the work done by the spring force. Remember, it's always the internal forces that are doing this work that is creating potential energy. And well, we've already worked this out once. The spring force points in the opposite direction from the displacement, so it's a minus kx times the differential element of displacement, which is dx, integrated from some equilibrium position where the x is equal to 0. That's where we're going to define our positions there, and then going to some final position x1. So the formula just becomes the integral of that, which becomes 1/2 kx squared. And here's a couple more questions. Piece of fruit falls straight down. As it falls, the gravitational force does positive work on it, and the gravitational potential energy increases. Gravitational force does positive work on it, and gravitational potential energy decreases. Gravitational force does negative work on it, and the gravitational potential energy increases. And the gravitational force does negative work, and the gravitational potential energy decreases. You can stop the video while you think about it and start it back up. Because the force of gravity points down and the object is falling down, the gravitational work is indeed positive. But since the change in potential energy is a negative of the work done by the conservative force, the potential energy decreases. A block is released from rest on a frictionless incline as shown. When the moving block is in contact with the spring and compressing it, what is happening to the gravitational potential energy U grav and the elastic potential energy UL? Well, what you have to know is which way are the forces acting. Gravitational force points down. So while this block is moving down at an angle, but the component of the displacement is in the same direction as the gravity force, or should I say another way, the component of gravity is in the same direction as the displacement, and so the work done by the gravitational force is positive, which means that it's losing gravitational potential energy, which hopefully doesn't surprise us since it's going down. What about the spring force? Well, the spring force points up as the spring compresses, and so therefore the spring is opposite the direction of the motion of the block. So therefore the work done by the spring force is negative, and therefore the spring potential energy is increasing. So the gravitational potential energy is decreasing and U elastic is increasing, so the answer must be D.